I've never seen a battery built more like a tank than this one from Discover Battery. I just took this one out of the case, and now we're going to take the second one out of its wooden case. And let me show you how this thing is even shipped. I mean, not only does the battery itself look like it's built like a tank, but it was shipped inside a wooden crate. So both of these were on the pallet and arrived, and I can't wait to test them out. Here we go. Hi everyone, I'm David, and I'm on a mission to take my house and garage off-grid. I collect energy throughout the day with my solar panels, but then at night I need to run the house and garage off of the battery bank. I have a couple of new batteries to test out. These are from Discover Battery, and this is their big 7.4 model, which is their 7.4 kilowatt hours that is stored inside this steel enclosure. I mean, this thing, it's pretty thick steel, and it's built like a tank. We're about to take this one out of the wooden crate, and then we'll, check our voltages. And one of the things I'm excited about these is they're supposed to talk with the Schneider inverter really well. But we're just going to test them like we do any battery we get in for a review on this channel. Here we go. So we have a wooden crate, and around all the corners are these tabs. Now these tabs down here on the bottom are facing straight, where you have kind of the skid. So let's turn this around. These two are bent down, so they're the ones that we need to bend forward. So I'm just going to tip this thing and try to get a screwdriver in there and bend that tab straight. There we go. All right, what do we get? Let's check it out. We got some stickers. This looks like a quality control sheet, and it has passed. This is our operating manual. We have this one over here, the large one. What else have we got in this sheet? So we have an Ethernet data cable. All right, we have a termination end. Looks like some splitters. Look at all this foam here. They really packaged this well. All right.
How much does this weigh?
This one's 87 kilograms. All right, so we got our protective caps on here. Right here it says USB, AE bus, and then Xanbus. Xanbus is the proprietary for Schneider equipment. And then we have some M8 bolts here. Let's check out what our voltage is. And this one is 53.26 volts. These batteries look pretty heavy, and they are. So I can't wait to test them out. We'll put a charge on them and see what we can do with them. Here we go. Well, the battery is now flashing a green LED on the power button. I think the BMS has probably shut off charging, and down here we have the charger flashing green. So it should be fully charged at this point. We're about to begin the capacity test of this battery. Down here, I zeroed out our meter, and I built this meter in a previous video. It has a shunt inside of it. So let's turn this battery on and check out what our voltage is. So we're at 53.9 volts, and I have a circuit breaker on here. So we got a 100 amp circuit breaker. We'll turn that on. That allows us to turn on this inverter. This is one of my first inverters I ever bought. 120 volts. And now we can turn on, this is a 1500 watt space heater. Alright, so as you can see, we're discharging a little over 28 amps at the moment, and 1.5 kilowatts. So this whole test should take somewhere around 4.5 hours. We'll of course keep track. We're recording the time right here. So as you can see, this is a 130 amp hour battery. It's a 16S lithium iron phosphate, which means we're going to have a nominal voltage of 51.2 volts, 130 amp hours, which gives us 6,656 watt hours. So this is going to take about 4.5 hours to discharge at our current rate, which we're currently doing 28.9. So the fan's just kicked on. This capacity test is still running. I expected it to finish already. We've got 133 amp hours. I thought we'd only get 130, and we're at 6.9 kilowatt hours in 4.5 hours so far of runtime. Now, it's supposed to be 130 amp hours and 6.6 kilowatt hours. Now, I know that it has 7.4 kilowatt hours total, but only 90% is supposed to be usable, but we're getting even more than that out of it. So we'll just let it run until it stops. All right, it just shut off. This is still beeping. Just died on us. Let's see how we did. 7.14 kilowatt hours, 138 amp hours. Excellent. The spec sheet says that this Discover battery can do 130 amps continuously. Well, we're going to test that. That should take about an hour to discharge, and I've got the whole test set up. We've got some 4-aught wire going from the battery to the Victron shunt. We're going to be able to monitor what the Victron shunt is doing through the Bluetooth app on this old cell phone. That 4-aught wire then goes into the Schneider PDP, or power distribution panel, which is powering up this Schneider inverter. I have just one Schneider inverter connected right now, and we're going to then be turning on a bunch of space heaters, just as many space heaters as is required to try to get us as close as possible to the 130 amps on the DC side. I don't want to go over that, but I do want to get as close as possible. After a period of time, as the voltage of the battery drops, I might have to adjust the space heaters to try to keep us below that 130 amp mark. But we'll try to run this for an hour, and hopefully it does not shut off due to overheating or something on the BMS. Now, the garage right now is a pretty nice 67 degrees Fahrenheit, so we shouldn't have any overheating issues, but we're going to test it and make sure. I adjusted the battery setting to 130 amp hours, and we are at 100% right now. So now we've got 100% state of charge, 53 volts, and we're drawing 33 watts for the Schneider inverter in idle. Nice big battery up here. We're at 100%, and let's begin the test. First thing we'll want to do is turn on this big water heater. Well, with that space heater turned on, we've got 121 amps. Let's try turning on this little one. 129 amps. I don't think I could have gotten any better than that. So we're just going to let this run as long as we can. Hopefully the BMS doesn't overheat inside the battery or something else happens. I will be out here in the garage monitoring this test as it's running, because I want to make sure I capture it right when it shuts off if it does, or if we start going over 130 amps, I'll turn off one of the space heaters. We want to keep it below 130 amps, but as close as possible as we can. It looks like the voltage is holding pretty steady at 50.4 volts. This test has run about half an hour now, and let's check out how we're doing. Well, excellent. Really nice, holding steady on the voltage, but we've gone up to 131 amps. So since we're over the 130 amp rating, I'm actually going to turn off this smallest heater here. And now we're below 130 amps again. All right, 56 minutes into the test, I'm going to plug in that thermal imaging camera, and let's see how hot everything got. All right, 1 hour into the test, and let's see how we're doing. And oh, it just dropped to 44 volts, 142 amps, just did it. Let's turn off our loads. We successfully did our load test. Here we go. Oh, and we had an event. That's for the low voltage. But I can't believe we did it. An hour into that test, well, 59 minutes. Well, the battery did it. It did exactly what I was hoping it would do and what I expected it to do. The specifications written in the manual say that it can run 130 amps continuous. Well, we ran it for an hour and it ran 130 amps. Yes, we were between 126 and 134 amps during the majority of the test, but it never shut off due to overheating or something like that. And I have had equipment in the past that cannot hit its own specification. So whenever the piece of equipment can hit its own specification, that is a big plus in my book. So I'm glad that it did that. Now we need to charge it back up and run another test. I just turned on my solar arrays and we're charging this battery at 104 amps. Most of the batteries that I test on this channel can only handle a half C charge, meaning that if you have a 100 amp hour battery, they can only handle 50 amps of charging current. This one can handle both a 1C discharge and 1C charge. Now that's a pretty high charge rate, and we're currently charging it at 104 amps, which is pretty impressive that the BMS is allowing that in. Now we might wind up hitting an over temperature alarm because there are a lot of temperature sensors built inside of this case, and everything is currently warm because we just did a duration discharge. So we might hit that high temperature cutoff, but I'm not sure. We're just charging with the solar right now. So far in our testing, this Discover battery is performing really well. We have done a capacity test, a duration test, and a surge test. Next, we'll do an overload test. The spec sheet says that this can do 300 amps for 3 seconds, and there's a 200 amp fuse built into it. Now we shouldn't blow the fuse if everything is working correctly, but hopefully we don't blow the BMS. Now I can't actually put 300 amps on it, but I will put a couple of very heavy loads on this inverter, and so we should get a little over 200 amps on the battery. Now since it's rated for 130 amps continuous, the BMS should shut off in a few seconds. I don't know exactly how long it will take, but we're going to find out together. What I want to make sure of is that we don't let the magic smoke out. I want to make sure we don't cook the electronics of the BMS. So if the BMS can shut itself off gently, and then maybe it will turn back on after that, or maybe I might have to manually shut everything off and then turn it back on. I want to make sure that it works after we run this test. Hopefully I don't kill it. Here we go. All right, and now I'll turn on the water heater. Let's see how long this takes. This is taking longer than I thought. Wow. Holy cow. I was really expecting it to shut off by now. This is a lot of amperage. My goodness. I seriously didn't expect it to last this long. I'm gonna have to put up a clock on the timer here. Wow, it's definitely been over a minute. I mean, I'm shocked it's doing it. All right, and there we go. It just shut itself off. And we lost signal because the BMS shut off. If I move this over, yeah, see the flashing LED? I want to see if the BMS will automatically turn itself back on. That was a really long duration. I'm actually really shocked that it handled it. That was over 10 kilowatts being pulled from the inverter on the AC side. I'm trying to give this a minute, see if it'll turn itself back on or if I need to manually turn it on. All right, sounded like it finally turned itself back on. Automatically, the inverter's turning on. All right, it turned itself back on. And the inverter still has the water heater. So the water heater kicked on automatically. That is great. So no damage to the battery. So this battery delivered over 200 amps. It felt like over a minute, but I'm gonna have to go back and check that footage for the exact length of time. And then it took about a minute for the BMS to automatically start back up again. Now that's great. We didn't let out the magic smoke. We didn't blow the fuse. And you know, I mean, everything just worked. We didn't blow the inverter. The inverter just came right back on again without needing any manual intervention. I didn't have to come out here. So imagine if this was in the middle of winter or something, and you know, I didn't have to put on my snow boots and trudge out here to manually switch on and off, or off and back on again, the circuit breakers. So really great job that it worked. Well, I think that's all of the load testing that we're gonna do on this battery. So next up, we're gonna try and make it communicate with the Xanbus network directly to the inverter, or technically it'll be to the Insight home and then to the inverter. So let's see if that works. So this battery has two ports on here. We have AE bus. This is for interconnecting multiple batteries together, and Xanbus. Xanbus is proprietary to the Schneider equipment. So these are RJ45 ports. There we go. So we're going to see what happens if we connect just one battery to the inverter for right now. So let's get this one going. Now the battery comes with one of these, I don't know, beige splitters. These are really inexpensive, kind of reminds me of what you'd see in the 90s. So let's put that in. And since this is similar to CAN bus, they need to be terminated. So the battery comes with a termination plug. And that tells it that it's at the end of the line. So as you daisy chain these items together, you need one at the end of the line. And the Insight home, this, is already self-terminated. So what we'll do is we'll take off the cover here, and we'll have to run an extra wire from the inverter over to the battery. And then we'll be able to check if the settings are automatically updated. So they'll be updated by going in and checking through Wi-Fi into the Insight home. So this is the PDP where all the circuit breakers are held, and this is the wireway. The wireway comes with the PDP and gets mounted underneath the inverter. I've removed the screws, and this gives us access to all the wires, and over here is where the communication wires exist. So underneath, we can see those are two Xanbus ports. And we're going to remove the termination plug that's in here. There we go. So I'm removing that termination plug. We'll just set it there for now. And what I can do is run a new Cat 5 or Cat 6 wire from that port. There we go, that's on. Now the other end of that Cat 5 wire will plug into the splitter. Now the inverter is running. So once this light turns a solid green, then we'll be able to go in and see what the settings are through Wi-Fi and our desktop computer. So it currently says that the battery's at 86%, and this popped up here without me having to do anything. I have not programmed it. All I did was plug it in, and you can see that popped right up. Now let's see what's going on here. Battery summary. This is history before I plugged it in. So here it says Discover AES. So this is the battery. Let's see what happens here. Great. So let's see what our maximum charge discharge ratings are. Configuration. Charger settings. So this is already set to 130 amp hours. That's what the battery is. Go advanced. Maximum charge rate is 100%. This could be adjusted down. So bulk voltage is set to 55.95. Absorption 55.95. Maximum discharge current is 184 amps for 5 seconds. Dashboard. All right, well, let's see what happens if I put a load on it. So I just put a load on the inverter. So it's 4.8 kilowatts. Over here, it's showing 91.2 amps being discharged. These batteries weigh about 200 pounds each, so you're not going to be wanting to move them around a lot. If you're using them for home storage, you might want to just sit them on a shelf. And, you know, I have a wood shelf behind me, and I might wind up doing that at some point in the future. Or if they're in an RV, you can actually through-bolt them through the flanges directly to the floor of the RV, and that would be ideal. But there is a third option if you're in a home storage situation, and you can wall mount them. There's an optional wall bracket that you can purchase. So let's take a look at this. It's nice thick steel, and you can see it's toothed so that it interlocks with the next one. This interlocking feature allows the wall brackets to share a stud, and the holes are lined up for 16-inch on-center studs, which is a very common stud spacing in North America. In my situation, I framed this garage 24 inches on center, so I need to reinforce the wall, so I'll be using an additional piece of 3/4 inch plywood. Now, I read through the manual that came with the wall brackets, and nowhere in here does it say that the plywood needs to be a fire retardant plywood or that you need to mount these on a flame retardant surface. So I'm going to use regular plywood. I'm going to secure it to this 23/32 OSB that I already have on here, and I will try to hit the studs that are behind here where I can, but I won't be able to put all 4 fasteners into a stud. So I'll be reinforcing it. I'll add a few extra fasteners, and it will be strong enough once I'm done. Now, if you're going to mount these underneath something like your inverters, they can't stick out more than 6 inches past the front face of the inverters or the circuit breaker box. In this case, I have a step because of the concrete stem wall that I have behind here, and then it steps back to the stud wall on top of that. So I can't mount these directly underneath my inverters. That's why I'm going to have them off to the side. You need to maintain the clearance underneath the PDP to gain access to the circuit breakers. Now at this point, I'm just going to use some regular screws just to tack this in place. These are not structural screws. It's just holding the plywood on until I get the rest of the project done. At this point, I'm just tacking it in place to hold it temporarily until I get the larger screws in here. So now I'm switching to 1/4 inch by 2 inch long lag screws. The manual says if you are going directly into studs, which would be in these outer holes, then you can use 4 1/4 inch long hardware. I think it said 3.5 inch long hardware. In my situation, I'm not going into studs, so I need to add 2 more. I need 6 1/4 inch hardware. All right, now we'll move on to the second one. And I'm using a drill bit that is a little bit smaller in diameter than the inside shank of the lag screw. That way the threads bite into the wood. Now I'll just remove my temporary screws. The wall bracket comes with two nylon insert lock nuts. With the batteries securely mounted to the wall, the next step is to wire these up to the inverter. As I've mentioned in past videos, I love bus bars. The ideal situation is to run a dedicated wire from each terminal on each battery to a central bus bar. In this case, I have a pair of bus bars up on the wall. So if I was to run an individual set of wires for each battery to the central bus bars, I would want all the wires to be equal length because we're trying to make equal resistance. And I would go for 2-aught minimum. So I'd use a 2-aught positive up to the bus bar, a 2-aught negative up to the bus bar, 2-aught positive, etc. Now that is the ideal situation. However, the manual does say it's okay to wire 2 batteries as a daisy chain, to parallel them down here using wires and then run a single wire up to the bus bar. So I'm going to demonstrate that, but I do want to push that the central bus bar is the ideal situation. So let's take a look at what considerations we are thinking about if we're going to run these together before running them up to the inverter. Now I have a big pair of 4-aught wire coming down from the bus bars, which are up at the inverter. So we'll just say these wires are coming down from the inverter. These are 4-aught. So if I'm going to run them down here, I'm going to have, say, the positive wire to this terminal, the negative over here, and then we're going to have little jumpers going between them. But I want those jumpers to be big. So I'm going to use some 4-aught jumpers because remember, each one of these can do 130 amps continuous. The bolts that came with the battery are M8 by 1.25 millimeter. These bolts have about 10 millimeters worth of threads to them. And if we check this terminal, we have about 16 millimeters of depth to the hole. So that hole is about 16 millimeters in depth. Imagine for a moment if you tried stacking 2 ring terminals using the bolts that came with the battery. As you can see, there's very little thread left there. And then you stack a second one. And what have we got there? 2 or 3 threads. So if I tried to do this with the bolts that came with the battery, I would most likely strip this bolt out. I wouldn't have the holding capacity necessary. So I'm going to be using some new bolts. These are still M8 by 1.25 millimeter thread, but the thread length on this bolt is about 20 millimeters. So we're going to have 6 millimeters taken up with the ring terminals, 3 millimeter thickness per ring terminal times 2. So we're going to have 6 millimeters taken away. That'll leave us with 14 millimeters. Since the hole is 16 millimeters, as I measured here, I should be fine. Now, if I can't get a good torque on this, then I can always add another flat washer and lock washer underneath the head of this bolt. But we should be okay. So let's give it a shot. Now remember, both batteries are off right now, which is one of the nice parts about wiring these batteries, that they have an on-off switch. That's still loose right now. Now over on this side, I can still use the factory bolt because we're just doing one. And again, that's still loose. The torque specifications are in the manual, but they're also printed right on the plastic lug here, and it says 13 Newton meters or 9.6 foot-pounds of torque. The power wires are now connected. As you can see, the wire going up to the inverter is on this battery for the negative and this one for the positive. Now it can be vice versa, but the idea is that you don't want both wires to the inverter on a single battery. I was going to say that the next step is the communication wires, and I started doing that when I realized there was one extra step that I need to do. So right now we have all the power wires connected, and I would love to put these caps on here, but with daisy chained, again, we can't fit the caps on with this unless I cut the caps. But if I cut the caps, they won't be able to snap around the ring anymore. So this is just another reason why running individual sets of wires to one central bus bar is a better solution. But right now we have one battery sitting here at 88% and another one at 91% state of charge. Now the voltages were very close to each other, so we were able to parallel them, but we need to top balance the batteries together. So right now they're both on, and they're run up to the central bus bar. So we're going to move the camera a little bit and I'll show you how I'm going to top balance them. Remember, they're all parallel together at the bus bar. The inverter is currently off, but these two batteries are on. And I just temporarily screwed this battery charger here, but it's wired up to the two bus bars. So we have our 4-out wires going to the bus bars and the inverter's off. So next what we'll do is we'll just plug this in right over here, and that fan just kicked on, or it will. There we go. So now that's blinking, and what that's going to do is try to charge them up to 58 volts. So one of the batteries will reach full voltage first, and then the other one will finish topping off. This is just a low amp charger, so we're not going to overload a single battery. But tomorrow they're both going to be 100% state of charge, and then I can remove that little charger and they'll move up and down together. So it's important to top balance them. So I didn't want to run the communication yet. I'm going to top balance them just as if they were lead acid batteries. But tomorrow, when they're both sitting at 100% state of charge, then we can run the communication. Now you could also do this independently. You could run this charger on each battery one at a time. I just like doing it this way. I allowed that charger to run overnight, charging up the batteries, and it looks like the BMS is actually shut off, probably due to high voltage, which means that now the two batteries are top balanced together, and I removed that charger. I should note that I'm doing one thing against the manual, and that is that I'm daisy chaining these with different length wires. When you daisy chain multiple batteries together, you want these jumper wires to be the same length or the same resistance. In this case, the negative is a little bit shorter than the positive. Now they are 4-aught wires, so we're probably not going to notice that the amperage difference between them, but I wanted to point that out. The manual says that you can have up to 4 batteries daisy chained together. Once you go to 5 batteries, then you really need to run to the bus bar configuration. However, I'm going to say that I think running each independent battery to a central bus bar, even if it's just 2, is a much better solution. But I wanted to demonstrate this. I wanted to demonstrate the wall brackets, make sure that you use a longer bolt when you have multiple ring terminals stacked. So I wanted to show this off. But once I'm done with this, I will probably be taking these off the wall and putting them on the wood shelves behind me. And then I'll run a independent wire from each battery to a central bus bar. So just keep that in mind when you're doing your own setup. At this point, we're ready for the data wires, the communication. So this little setup with the short Ethernet jumper and the splitters, and don't forget the terminators on the ends here. This is going to let me join the 2 batteries together. So the 2 batteries will talk to each other using the AE bus RJ45 port so that they'll communicate up as one big battery bank to the Schneider. So this is on the AE bus. So when I mount these batteries over on the shelves behind me, I'll be able to really protect all these wires inside the framework of the shelves. So once all the batteries are daisy chained together on the AE bus, so they communicate as one big battery bank, we can have just one connection up to the Schneider equipment. So in this case, I have one more splitter with one more terminator and the Cat5 wire going up to the Schneider. So that's on the Xanbus port. So it's still an RJ45 port, but that's specifically talking Xanbus, which is the Schneider proprietary system. The circuit breaker of the Schneider is on, and I will just press the little power button and turn on the batteries. I don't think the order of how you turn them on matters. So now I need to wait a couple of minutes for the Insight Home to boot up, and then we're going to log in, look at the Insight Home, and we should see the 2 batteries communicating as one big battery bank to the Schneider. Let's look at our battery. All right, we're currently showing 100% state of charge. A little bit of current is being consumed just to keep the inverter on. And over here we can see 280 amp hours. So it did successfully upload. Let's go configurations, see charger. Yep, 260 amp hours. That's excellent. So it looks like everything is good. All right, let's go ahead and turn on some loads. And as you can see, we've got 4.5 kilowatts going out to the water heater that I just turned on, and 4.7 coming from the battery. All right, so once again up here we have 91.5 amps, and over here we have 48 amps, and over here 44.92. 48, 45. So about a 3 amp difference between the 2 wires. So one battery is going to be getting 3 amps more than the next. And that's most likely this one here, because this one has a little extra resistance on this wire. Now they'll equal out once I take away the load, but this is amazing really when you consider how thick the 4-aught wire is and how minimal the difference is. And so really going to a bus bar configuration is the best way to do this to make sure that the batteries get equal use. Imagine all these connections going down a line. My favorite part about the data communication here is that it truly was plug and play. I plugged in the wire between the battery and the inverter, and that was it. I logged into the Insight Home simply to verify the numbers, but at no point did I have to enter a serial number or create an account or scan a QR code or anything like that. And that I love that about it because I'm not great with computers. So if you can eliminate me having to work with a computer, that is really great. So good job to Discover Battery to actually make something that truly is plug and play. Way too often we get sold the advertisement of something being plug and play, and then it's not. We actually have to do something user interface with it. But in this case, we didn't. Now, I love that this is actually a UL listed product. I mean, they've got multiple UL listings for mobile applications, for home storage. They've got the special UN something 93, I think it was, listing for the batteries and the Schneider equipment together as one certified energy storage system. The BMS was outstanding. I mean, we did 219 amps for a minute. I mean, that's incredible. Typically, something like a BMS is going to shut off as soon as you go a little bit over its rating. So I was really impressed at the overload test. If I was to nitpick, I would say that they got it 99% of the way there, but that 1%, having to use a splitter on here, instead of having two Ethernet ports for the Xanbus and two Ethernet ports for the AE bus, I don't like having to use the extra kind of beige homeowner splitter here. To me, it seems fragile, like I'm gonna hit it and break it off. I wish that they had sent two terminators for the CAN bus instead of just one with each battery, because they are something that, you know, the inverter came with one, which I still had. I hadn't lost it, so I was lucky there. But if I had lost it, I would have needed to order a new a new terminator. So I'm not a fan of daisy chaining batteries, but if you're going to do it, please remember that all the wires need to be equal length and you need to get longer bolts. I think these are probably brass terminals built into the battery. So when you're driving a stainless steel bolt into there and you put any stress on these wires, if you don't have enough threads engaged, you're going to strip it out. So I'd really like to see those longer bolts if you're going to daisy chain these and stack your ring terminals. Now in the current configuration, I can't fit these plastic covers on, but these plastic covers look really nice. So all this to say, I don't think wall mounting these is the best bet for these batteries. I'll be moving them over to the wood shelves. I'll be running a 2-aught wire from each battery to a central bus bar. Now let's talk about kind of the elephant in the room. These are rather expensive batteries if you're looking at them per kilowatt hour. So these will cost about $600 per kilowatt hour currently at this time that I'm filming. And you can purchase other server rack style batteries for about $300 per kilowatt hour. So these are twice as much per kilowatt hour. So who's going to want these? Well, somebody who wants a truly UL listed product with the UL listing stamped right on there. Somebody who's concerned about having the highest level of safety possible is going to want these batteries. Using these combined with the Schneider system gives you that level of safety and comfort knowing that it's a full system all integrated together. Now the other customer base that I think would be interested in these is going to be the mobile application. Van life, tiny house, and RVs. The flange on the bottom built right into the steel means that you can through bolt this and have a really secure, solid connection. So no matter how many vibrations while you're driving down the road, you'll have confidence knowing that this battery is not going to go anywhere. So I love this for that application, and it's got the UL listing for that application. Given the price per kilowatt hour, these batteries won't be on everybody's list if you're a DIYer. But if you're really looking for a rock solid battery that has the UL listing, has the energy storage certification, or you're in a mobile application and you really want something secure that can handle the vibrations of driving down the road, then consider these batteries. Check them out. Well, thank you everybody so much for watching. If you enjoy these videos, please like, subscribe, comment, and share.